Hi, and welcome to the fourth video in a series about differential forms. And in this video, as you can see at the top, we are going to be taking a look at the tensor product. So the tensor product is going to be a product operation on the set of all tensors on a vector space V. Note that not just k-tensors or tensors of the same order, but in fact it's an operation defined on all given tensors that one can construct on a vector space. And we will take a look at it. So this is going to be quite an exciting video because it's an important definition. It has very cool notation, and hopefully you'll find it as fun to write as I do. And what's funny is I was looking at my very old YouTube videos from about 7 years ago almost, when I was making videos on just scalar and vector quantities in general and in physics. So it's very cool to me that I'm now 7 years later making videos on tensors and tensor products on these spaces. So let's take a look at it, where we take the product of a k-tensor and an l-tensor, and we want this to be a k plus l tensor. So it's constructing tensors whose order is the sum of its constituent product tensors, right? And its formal definition is that if we let f be a k-tensor and if we let g be an l-tensor on V, then we define this k plus l tensor f tensor g on V, which is given by on the set of k plus l vectors. We define it as how f acts with respect to all of the things that it is linear or multilinear on. So f acts as a k-tensor, g acts as an l-tensor on this quantity of k plus l vectors, and you just take their product afterwards. So this is the tensor product because it is a product operation on two given tensors, as follows. In this video, I think we're just going to be looking at some of the properties of the tensor product, and it'll be very brief because what's really good is for viewers to prove these on their own just based on this definition itself. If need be, I will actually publish just a follow-up going through the proofs of these four statements that I'll put forth, but hopefully they'll be fairly straightforward. And that'll be this video, a short one, where I just give this definition, and then in the one afterwards, I will give a deeper understanding of the action of a linear transformation and how tensors behave with respect to linear transformations of underlying vector spaces, right? So that'll be the next video. So this is our tensor product definition, and let's look at some of its properties, which I will state as a theorem. If we let f, g, and h be tensors on V, not necessarily of the same order, because remember, you can have a tensor product on different orders, k plus l here. So if we let these be tensors on a vector space, we show that the first one is associativity of the tensor product operation. So f tensor and then g tensor h is the same as taking f tensor g and then tensoring that with h. That's associativity. The second one is homogeneity. So we show this triple equality that if we take a scalar c times f tensor g, if you evaluate this, you can just pull a scalar out of a tensor product as follows: c times the tensor product of f and g, and this equals f, the tensor product of f and the same scalar c times g. So you can place the scalar anywhere you'd like basically in this tensor product, and that's essentially what we have. So this is homogeneity. And the fourth one we have is distributivity under a certain restricted condition. So if f and g are, let's say, k-tensors or tensors of the same order, which we require, then we have these two distributive laws. So f plus g being these two k-tensors, itself being a k-tensor. So we want this to be having the same tensor rank or order. We take it with some h, which is an arbitrary ordered tensor. So this does not have to be in accordance with that of f and g. It distributes like this. So in some sense, the tensor product operation is analogous to that of the distribution of multiplication, just regular products over sums. And the second one is showing that it holds the other way. So maybe you might be familiar with, like in the definition of a ring, one must show at first, if we're assuming nothing more about the structure of a ring, for it to be two-sided distributivity, because there's no guarantee your ring is commutative. And in fact, the tensor operation, so f tensor g, is almost never equal to g tensor f. So it is a very, very rarely commutative operation. Hence, we must specify this to be true in both situations, and these two quantities need not be equal to one another. So it distributes in this way as we would expect. And the fourth proposition has to do with our formulation of a basis and looking at multilinear transformations and characterizing them based on how they act like this. This one's a bit different from the prior three. So given a basis a1 through an for some vector space V, and we take I to be this indexing set as before, to be I1 through Ik from this indexing set of n integers, so 1 through n, we want to characterize the phi sub I tensor as the product of elementary tensors. So in this case, it's k-tensors. In general, it need not be. The corresponding elementary tensors will satisfy this equation, where phi sub I being the k-tensor that is defined like this. So phi sub I can be broken up in the tensor product of its constituent elementary tensors, so phi I1, phi I2, so on through phi sub Ik, depending on the indexing set that's used based on basis elements, right? So we have this this kind of representation or molecular look at elementary tensors and how they form a basis for the space L to the k of V, for example, for k being the order of a tensor. And we just condense this tensor product notation like this. So we have this tensor product, so this index j equals 1 to k is equal to phi sub I sub j. And these are our four propositions. It is good to show these, and if need be, I will publish a second video just going through these proofs in more detail. But hopefully you can look at them and deduce these properties. So this is the idea of a tensor product. And I'll keep this video short. It's like 7 minutes, so much shorter than the others that we've done in this series. In the next one, we'll look at the idea of a linear transformation. I think there's going to be a lot of diagrams involved there, and a deeper look at what's going on. And I think afterwards, we're going to look at specific kinds of tensors called alternating tensors. And these will be the ones that we're most interested in. So alternating tensors, which we'll define, and we will actually take a look at some group theory about the symmetric group in particular and its structure. So typically one doesn't need a whole lot about the symmetric group and permutations to look at alternating tensors, but I just want to do a separate lecture, almost as an abstract algebra kind of introduction to it, just in general. So we're going to look at alternating tensors after that, and we will continue on our video series about differential forms. So hopefully this was clear. Hopefully these proofs are not too one can go through these proofs on their own, and I will see you in the next video. Thank you for watching.